So kind of the first thing that what we were in the middle of at the time was singularities. Right, and so one thing that was included on the last exam was this Riemann's removable singularity formula of theorem. Right. So that was the statement that if you have a singularity and your function is bounded in a neighborhood of that singularity, then that's actually a removable singularity. Okay. So and that like almost everything in this course was a consequence of the Cauchy integral formula. Okay. So Cauchy integral formula. That's how you get the Riemann removable singularity formula, and that in turn gave us like the characterization. We had this characterization of poles, right? That you have a pole if and only if your function goes to infinity, as z goes to the pole, right? So that was proven using Riemann's removable singularity formula, theorem, and also Casorati-Weierstrass. Casorati-Weierstrass, which said that if you have some essential singularity, then you take some neighborhood. Take some punctured neighborhood of that thing, then that was going to be dense, is dense in C, right? So that's that was also obtained from Riemann's theorem, as was this theorem about meromorphic functions. So that meromorphic functions on the extended complex plane were exactly the rational functions. Okay. So we basically just sort of finished up this business about, these were the last things we said about singularities. And then from at that point, we sort of jumped to basically consequences of the argument principle. So there's like all sorts of like fine properties of holomorphic functions that follow from the argument principle. Right. So over here, the argument principle, which we got as a consequence of the residue theorem, right? Right. Plus basically logarithmic differentiation. That said that if you look at this sort of integral, then you get something that tells you about the number of zeros and the number of poles. Right. So that was the argument principle. The argument principle gives you Rouché's theorem, right? So Rouché's theorem, remember, is saying that if you take a function and then just perturb it a little bit, then the number of zeros doesn't change. And then from Rouché's theorem, that got us from Rouché's theorem, we got the open mapping theorem. Okay. Right. So we right. So yeah. So kind of at that point, we sort of jumped and we we talked about the deformation theorem, which was about homotopic functions, homotopic curves. Right. So this was the theorem that said that, right, if you have two curves that are homotopic to each other, then if you have a holomorphic function, then the integral doesn't depend. Then the integral over curves that are homotopic are the same as each other. Right. So I should say that the proof of this is pretty long and complicated. Don't worry about the proof of this one. Okay. So don't feel responsible for that, because it's just too long, and I don't think it's particularly insightful. Yeah.
That was one of my favorites.
Oh, really? I mean, I really liked it. I mean, not to say I don't like it, but I think
the picture looks great. Yeah.
yeah. No, it's cool. It's brilliant. But I think it's sort of like the argument is very specific to the theorem, and yeah. Okay. So so this is kind of where we were, and then at this point, I wanted to go backwards a little bit, and so I introduced the Laurent expansion, because I thought it was kind of wrong not to include this. So the Laurent expansion, which again is an immediate consequence of the Cauchy integral formula. And from the Laurent expansion, that gave us sort of another way of thinking about of Riemann's theorem. That that in fact a singularity is removable, right? So a singularity is removable. Right. If and only if the limit of z minus z naught times the function is 0, right? As z goes to that thing. Okay, so that that gave us a different sort of like a slight extension to Riemann's theorem. That was handy because that gave us this sort of like extended version of Cauchy-Goursat. So remember, Cauchy-Goursat tells you that if you get this holomorphic function, and a function that's holomorphic on a curve and inside it, then when you integrate, you integrate over the curve, that you get 0. And so the extended version is basically saying that as long as you've got removable singularities in there, then that will also, then you can still use Cauchy-Goursat. What that was useful for was, so we also introduced this sort of geometric idea of the winding number. Right, the winding number of a curve. Right, so you have some number of a curve about some point. How many times the function winds around that point. And so the extended Goursat basically gives you this sort of like Cauchy integral formula plus winding. Right? That if you have an arbitrary curve, right, you have an arbitrary curve, you look at you look at the standard thing, but now instead of your curve just going in around a disk or something like that, it can basically do anything, and what you end up with is the winding number times the value. So it gives this sort of like more general formula, which is useful. Okay, so yeah. Right. Okay. And so, and from there, well, the picture gets kind of bad here, but I threw in a couple of extra theorems that are important. So both are consequences. They follow from Rouché's theorem. So the first one was this so-called n-to-1 lemma. This n-to-1 lemma that said that locally your function is going to be, if you have a holomorphic function, then basically that function is locally n-to-1, right? It covers, right? So you have some point here, and it gets mapped to some other point. Then it's possible to find a neighborhood here that gets covered n times by some other neighborhood here, right? So that was this n-to-1 lemma. The proof of it is actually the same as the open mapping theorem, and you can get the open mapping theorem from the n-to-1 lemma. Sort of obviously, they have almost exactly the same proof. So yeah, so Rouché's theorem gives the n-to-1 lemma. So it's kind of a sine route that we probably should have taken when we went back here. Go through the n-to-1 lemma. You've got this kind of strong theorem. You can use that to get the open mapping theorem immediately. Open mapping theorem. I don't think I put it down. Open mapping theorem gave us the maximum modulus principle. Right, gave us the maximum modulus principle. Another thing that we sort of threw in from the n-to-1 lemma was this theorem of Hurwitz's theorem that said that whenever you have holomorphic functions that uniformly converge to some function, then the zero of this thing is realizable as the limit point of zeros of these guys, right? So like the zeros for the zeros for the limit are limits of zeros of the f sub n's, roughly speaking. Okay, so that was Hurwitz's theorem. So these are all sort of like important facts about holomorphic and meromorphic functions. This is basically like closing all the basic knowledge of holomorphic and meromorphic functions. Okay. Yeah. So singularities, and then these consequences of really Rouché's theorem. But if you dig back, then Rouché's theorem comes from argument principle. Argument principle comes from residue theorem. Okay. So. Yeah. So when you're thinking about the exam, maybe just see if you understand like how things go, right? Like how does this how does this give you this? How does this give you this? How does this give you this? Just make sure that you can track all the paths. So, so that was sort of like closing the book on the basic facts about holomorphic and meromorphic functions. And then we said, okay, now we're going to go this kind of, we're going to bring in Fourier series and the Fourier transform. So we started off with this theorem. Relating, there's this theorem relating holomorphic functions. And Fourier series. So we started off with this theorem that said, if f is holomorphic on some interval, sorry, on some disk, well, then the power series coefficients of the power series expansion of f are related to the Fourier series, related to the Fourier coefficients. So a sub n for n bigger than or equal to 0, the power series coefficients are 1 over r to the n times the Fourier coefficients of right. So these, I think, I hope these look a little bit more familiar to you now, right? These are just the Fourier coefficients, right? So relating the power series coefficients of the relating the coefficients of the power series expansion to the Fourier coefficients of these functions. So that was the first thing we did, and as usual, it's a consequence of the Cauchy integral formula. So I remember when I was preparing in graduate school, when we were all studying complex analysis together, basically you realize that everything is a consequence of the Cauchy integral formula. Or if you want to step back one step further, Cauchy-Goursat. Okay, so that's if you can start from there, then you can get anywhere, basically. Okay, so now this theorem here actually gave us the mean value principle, mean value property of holomorphic functions. Right, just the case when n equals 0. The case of n equals 0 is the mean value property of holomorphic functions. And then when you take the real part of this, that gives you the mean value property of harmonic functions. So immediately that gives you the mean value property of harmonic functions. Because every harmonic function can be realized as as the real part of a holomorphic function. So we use that fact. Okay. In some texts, sometimes people prove from here the maximum modulus principle. So you can actually go from there to the maximum modulus principle. So slightly different route. Okay, so right, we're basically connecting. Right, chapter 4 is connecting, Fourier analysis with complex analysis. Right, and the main thing is to get the Fourier inversion formula. But before that, we did some kind of an easy connection. So there's this sort of easy connection using Cauchy-Goursat, which gave us that if f was holomorphic in a strip, then the Fourier transform has a certain decay. Right? Then the Fourier transform decayed exponentially. Right. So relating, like this whole chapter is to talk about the relationship between holomorphicity and the Fourier transform. Right. So yeah. So this was sort of like the first step along the way, and then we sort of jump away from that and talk about just we use of course the Cauchy integral formula to get the Fourier inversion formula. Cauchy integral formula plus Cauchy-Goursat, which in some sense are the same thing, to give us the Fourier inversion formula, right? Right. You use the Cauchy integral formula to get an expression for the Fourier inversion formula, and then you shift it, right? And then you shift it using Cauchy-Goursat. Okay. So yeah. So and then after that, we went for this other. We used the residue formula plus Cauchy-Goursat again, the shifting of the contour to get the Poisson summation. So yeah, I think, let me say, for the exam, don't worry about the proof of the Poisson summation formula, because it's pretty, the techniques involved are pretty much the same as in the Fourier inversion, except that you're using the residue formula. But yeah, this business of shifting the integrals and stuff, that's basically the same. So if you guys understand the proof of the Fourier inversion, then that's enough. Okay. Okay. Yeah. So yeah, right. So Fourier inversion. Right. So from the Fourier inversion formula, maybe let me just move this to the side here. So. From Fourier inversion, we were able to get this sort of a converse statement to this one, right? That if the Fourier transform decay properly, then f could be extended to a holomorphic function on the strip. Right, and so this was kind of an easy extension. This was an immediate extension, basically saying that the trick was to use the Fourier inversion, just use Fourier inversion. That was basically it. So, right, you start off with your function, right? Your function, you can recover using the Fourier inversion formula, right? So e to the 2 pi I x c, right? You can recover your function using the Fourier inversion formula, and then basically you say, well, I'm just going to I'm going to just extend that to the complex plane by allowing a complex variable here. By allowing a complex variable. And sometimes this is called the holomorphic Fourier inversion. That's kind of a misnomer. The idea is simply that you take the inversion formula, which is valid on the real line, right? And then you say, suppose we use a complex variable instead. We'll get something which is by definition equal to the function on the real line, right? By the Fourier inversion formula, right? And then you need to show that thing actually is holomorphic, right? And that's done in depending on the situation. That's done in different ways. So So this okay. So that trick is used a couple times in this section. Fourier inversion formula comes from Cauchy-Goursat and also Fubini's theorem. We did need to invoke Fubini's theorem. Okay. So the maximum modulus principle can be used to give us Phragmen-Lindelof. Right. So remember, Phragmen-Lindelof was basically the maximum modulus principle, but on this unbounded sector, right? And then Phragmen-Lindelof plus Fourier inversion gives you Paley-Wiener. And we had two versions of Paley-Wiener. There was one where the support of F was contained in some bounded interval, and there was another one where the support of F was contained in zero infinity. Right. So this was the one where you could extend your function to an entire function, right? Entire function in the plane with certain growth, and then this was the one where you could extend it to the upper half plane, right? So these are apparently the two original theorems of Paley and Wiener. They're the classical Paley-Wiener theorems, and then there are variations of them that came later. Okay, so that's what the exam will be on. That's what the exam will be on. Do you guys have questions on anything? Do you want to talk about anything? Yeah, so for this one, we didn't go over the proof. The proof is only barely sketched out in the text, so of course don't worry about the proof of this last one.
But the minus m to m1?
The minus m to m1, let me think about that, because that is also a huge long proof, but it's also super important and has ideas that are, I think, important for anybody interested in analysis. So of course I'm not gonna ask you to prove the whole thing. That would be, you guys could rightfully just attack me at that point. I think I would just die willingly. Yes, you're right. Right. It's like
Just one question.
Yeah, or maybe I was thinking maybe for the exam I should ask you to prove the second version. Right. Because then you'd have to have mastered the proof of the first one. Yeah, I would I don't know if any of you guys watch Rings of Power on Amazon,
Oh, yeah.
but I would die like the Lord of the Orcs at the end. Yeah, that's how I would die. Yeah. Maybe I'll tell you what I expect you to know from that, because there's a lot of important things in there. So maybe I'll just sort of break it down and say you should understand these steps. Okay, so that, but not, I'm not going to ask you to prove the whole thing, but I think there's some really important parts there that I mean, some of the steps are dull, but for example, showing that the perturbed, the epsilon perturbed functions actually satisfy a stronger bound. That's sort of like dirty hands kind of level analysis. It's not that exciting, right? But to show, for example, that their Fourier transforms are 0, that's actually important and involves some useful ideas. To show that their Fourier transforms converge to the Fourier transform of the original, I'm not sure if I would ask that, because that relies on, that's a simple consequence of dominated convergence, right? So, dominated convergence isn't really something that we've spoken of much. So, yeah, I'll try and send out something that indicates what things I think you ought to know. Yeah, I mean those are those 2 points. Yeah, let me think about that.
The one key point was to show that
the Fourier
transforms are 0, and the other one is what?
Well, so the other one is that their Fourier transforms actually converge to that of the original function. But that's a consequence of dominated convergence.
Right.
So maybe I should ask that, but it's simply that you can change because of dominated convergence, you can change the order of limit and integration, and then the limit of those guys just returns your original function. So. Yeah. That's all I prepared. Yeah. Yes, Joseph.
This is a bit of a meta question, but other than the Laurent series material,
Yeah.
Is there anything that was not in the book, or is all of the stuff that you've covered so far just coming from the book? I can't quite remember.
Everything except for Laurent and the N-1 and Hurwitz. So I think I have not sent you that. So let me make sure that I do. I also forgot to mention the construction of the branches of the log. So that's sorry, I should have mentioned that. Right? Like so, the logarithm function, and also complex powers. So, yeah, but that's basically it. So the Laurent series, the log as a multiple value function, complex powers. Complex powers are not exactly. Stein does it basically using only the principal branch of the log, and when we talked about it as multiple value functions. So. Yeah, and then N-1 lemma and Hurwitz's lemma. But I'll be sure to send you that stuff. I'm pretty sure it wasn't in the gigantic mass of notes that I sent you yesterday.
Will the format of midterm 2 be?
Yes, the same. Yeah,
okay.
Yeah. Roughly the same. Yeah. Maybe there might be less in the true-false section. Yeah. I see that gets some positive reaction. Yeah. Yeah. Okay, that's it. Unless people have more questions. Do any people have more questions? Okay. Okay. See you guys on Monday.
Yeah, we got lots of routes to go.
What's what, this?
Oh, is it the OMA?
We're not there yet, but I was like, we could practice where we have to like go ahead. Like we have like a
Functions
For-
and stuff.
yeah.
That's very important.
Oh, green and Krantz?
Yeah.
And I was looking at it, it's nice to see some of the overlap already.
Yeah. That's a good look. It does things so. It starts off really weird, and that's why I didn't use it. It starts like the way it presents the basic material is just bizarre.
Oh, yeah.
Yeah, but then once it gets past the basic material, it's actually really lucid. So yeah.
Like I like being able to see like the differentiation operation and being like, oh, I know all of these parts now.
Yes.
Okay.
Yeah, he basically wanted to do it from a multivariable calculus perspective. So yeah, and he does, but it's just, I think it's prettier if you do it a different way.
Oh.